Hello and welcome to the next episode of Adding Houdini to your arsenal. Today I want to start something new. I want to have a look at simulation. Until now we had a look into vanilla SOPs. We did procedural modeling, looked into VOPs to build our own operators, and even into shading with Redshift. And today I want to introduce you to DOPs, to the simulation framework of Houdini. And to make the transition easier, we want to start with a SOP solver. The SOP solver is the DOP network encapsulated such that you can use it in SOPs. But first, what is simulation? Well, inside of SOPs, you create a geonode. Let's put one down, and then let's dive inside, and inside we create a sphere. And now we can append a WOP, a point WOP. Like so. And if we now make the point WOP visible and dive inside, I have here the parameters, and I can control them. So I can lay down a constant, say, switch the type to vector, and let's say 0, 1, 0 for now, so 1 unit in Y. And as soon as I connect this to P, the sphere jumps to this very position. So now it sits at 0, 1, 0. If I scrub the timeline, nothing happens, because this is of course not dependent on time. I'm just setting this value in every frame. So in every frame Houdini generates a sphere, passes the geometry on to this point WOP, executes the point WOP, and finds this value here to set it. If I want to animate this, I somehow have to make this dependent on time. And I can do this by using one of these time variables here. I have this time port and the frame port. The difference being that the time port is giving me the time in as a float, and the frame port is giving me integers. So let's say we lay down a multiply, and let's multiply this vector here by the frame, like so, and use this result as a new position. Not much changes, because on frame 1, this vector times 1 is just this vector. But if I now press play, you see the sphere is taking off like a rocket. And that is because in every frame, this constant will be multiplied and will grow more and more. It's a little fast, so let's maybe decrease the magnitude of this vector. And you see, this is how I can achieve an animation. Now, the entire thing is time dependent. But it is not a simulation. The difference being, a simulation is based on the results of the previous frame. So instead of directly setting the value, multiplied by time or not, I want to use the results of the previous frame to generate the results of this frame. How can this be done? Well, instead of just multiplying this constant with the time, what I could try to do is, I could just read the position of the sphere, then add something, say let's add this vector here to the current position, like so, and then use this as a new position. You see, the sphere jumps up. And now if I press play, nothing happens. Because this idea is exactly the idea of simulation. I'm using the old position, so I'm reading the position, adding something to it, and then using the result as the result of my frame. Unfortunately, SOPs do not work like this. In SOPs, there is no way to read the value of the previous frame. Instead, this entire point WOP is initialized on every frame, and the position here that comes out of this port is initialized to whatever comes in here from the previous node. So this is not how it works. Nevertheless, in Houdini, there is a way around this, and this is the solver node. So lay down a solver here directly inside of SOPs. This node here with this little brain icon, and what this solver does is it provides us with a way to read the values from the previous frame. So now what we can do is we can connect the sphere to the solver. And then let's take this point WOP, just cut it and paste it inside. And inside you find these 5 nodes here. These 4 nodes are just referring to the 4 input ports. In reality, these are just plain old object merges that use a op input path expression to read from the 4 inputs. We don't need them for now. But this purple node here, that one is interesting because this one reads, using some very complicated Houdini magic, this reads the values from the previous frame. It gives you the geometry from the previous frame. So if I now connect this here, the sphere appears because it is reading the sphere from the previous frame, but with the difference that it's now reading the value from the previous frame, because this operator is initialized with the value that comes out of this previous frame node. And if we now go up 1 level, go back to frame 1, you see that now I created my very first simulation. The sphere again is just moving upwards, but now not because I'm using the time variable, but instead because I'm adding to the position over and over again in every frame. So now let's try to do something useful with this. Let's keep this sphere, but let's switch it to polygons. Or polygon mesh, say, and let's up the resolution to something higher. Well, not that high, let's say 48. And now I want to remesh this. So append a remesh node to turn this into nice triangles. And the remesh node should be set to 0.1, say, to give us quite some triangles. To make the result a little more even, let's up the iterations to 3, like so. And now let's feed this into the solver. Make the solver visible and dive inside. So now, inside, let's get rid of this point VOP. Instead, let's think about doing something else. The very first thing I want to do here is to append the mountain. Like so. A mountain sub, to give it some more interesting shape. And now I intend to grow this geometry. But I don't want to grow it evenly in all directions. Instead, I want to grow it only there where the curvature is high. So let's first measure the curvature. For this, there is a node called measure. It not only is able to measure the curvature, but other properties too, like the perimeter, the area, the volume. But we are interested in the curvature. If you just set this node to curvature, it will give you curvature values, and you can see them if you just switch to the geometry spreadsheet, and there this attribute curvature appeared. And this curvature here is the curvature of our object. Now let's make this curvature visible with a color node. Let's append the color node here, make it visible, and then switch to ramp from attribute. The attribute we want to visualize is curvature, like so. And now we have to increase this range here, and you see this is a curvature. So in areas where the curvature is concave, the value is low, so it's black or dark, and with convex curvature, the value is high, up to 26 or something. The value range is really hard to determine with curvature due to the mathematical definition of curvature. Great. So first go back to the measure node, and let's switch this to curvature type convex. We only want to measure the convex curvature. That's more predictable. And now, before we continue, let's blur this. To blur an attribute, we can use the attrib blur node. Attribute blur. This can be used to really blur every attribute that we want to. Connect this to the color and up the iterations to say 3. But at the moment it's operating on P. That is not what we want. We want it to operate on curvature, like so. Now this is blurring out the curvature quite a bit, but that is great because otherwise we have a hard time with all these sharp curvature jumps. And now let's generate a VOP operator that displaces this surface, taking the curvature into account. So lay down a VOP, point VOP, append it here, and call this displace by curvature, like so. Make it visible, dive inside. Now the very first thing we want to do here inside of this VOP is to displace the surface. That can be done by using a displace along normal node. The displace along normal node expects a point or a position and a normal. You can give it just the normal n. And then it generates a point or a position that is displaced along this normal. So if I now connect this P here, I get a displaced vector. And here I have this parameter called displacement amount, and if I move this slider, you see that the entire surface gets displaced along the normals. That is exactly what we want. It's just that we don't want to use a uniform amount for all the points, but we want to base this amount here on the curvature. So let's bind the curvature. By using a bind node, we can bring in an attribute, and as the curvature exists on the point, it's easy because we just have to type curvature here, and we have the curvature inside of our network. Now we could connect this curvature directly to the amount port, but that is not very predictable. As I told you, if we have a look at the geometry spreadsheet and then just sort this curvature value, you see that the range is really not very predictable. So it really starts, it has values here in the 6, 7, not very predictable. So instead, let's append a fit node here. With a fit node, we can change the range of the curvature. Sorry, I connected the wrong port. The first one goes into value. And now let's say that we want to take the range between 0 and 6 and map it to the range 0 to 1. Great. Now we have normalized this curvature range, and now we can append a ramp parameter. And this can be used to generate an interface to be able to reshape the value range. So switch this to spline ramp, because it is a float that we are dealing with, and connect it here. Now this gives us an interface element called ramp on the level up. If you expand this, you get a nice GUI, and this defaults to 0, so drag this right point up. Now this range here does not alter what we did before, because 0 maps to 0 and 1 maps to 1. But now we can change this curve to generate different results. And what we intend to do is just to use a very high curvature range to drive our effect. So let's move this slider here over to the very right to really transform the range to 0 everywhere but where it is already high. After doing this, dive back in. Now we can visualize what we did here by just connecting the ramp output to CD for now, just as a debug tool. Sorry, again, wrong connection. Like so. And you see, that is a result of this curve. You can watch this interactively. So this is the curvature that we are starting with, and after the remap operation, we are left with curvature values around 1, only in the areas where the curvature is very high. That is exactly what we need. But still, before we connect this to the amount, let's fit it again. Because at the moment, it's outputting values between 0 and 1. That's a good thing, because 0 and 1 is the range that this ramp is operating on. But we want to determine the strength of the displacement amount. So this second fit goes into this amount, and it's far too strong, as you can see, because the destination max is 1. But now we have a chance to change this, say, to 0.2. So now we have only a very slight displacement effect. So great, nothing special so far. But remember that we are inside of a subsolver, and that means that we can feed the result of this operation, of this geometric operation, into the next frame and use it as a starting point for the same operation. And this will lead to very interesting results. But before we do this, let's go up one level and let's test out what we have so far. If I press play now, what happens is a very, very ridiculous simulation. Because it's now doing the same thing over and over again. So it's calculating the curvature, then using the curvature for the displace operation, and you can see that only the white areas get displaced. And then it's feeding the result of this second frame into the third frame as a starting point and doing the same thing again, displacing along the curvature, which quickly leads to very chaotic behavior. Nevertheless, quite interesting. So how can we enhance this behavior? Well, we can remesh this thing in every frame. So go back into the solver and append a remesh node at the end. And let's turn down the target edge length to 0.1 to make it a little bit more even. And let's try this again. So what happens now? Maybe click on this stopwatch because this forces Houdini to play the simulation in real time. Okay, now this is a little bit more interesting. It gets slow very quickly. That is because the remesh mode is not very fast. And as soon as this thing grows bigger, the remesh node takes a longer and longer time to execute. But now this gives us a very interesting shape, because now something different happens than before. Again, this is a simulation, always dependent on the previous frame. So in the very first frame, we are calculating the curvature, and then we are displacing the areas that have high curvature. And in the next frame, we generate a new mesh. So now we have more polygons to work with. That means that the next step is far more predictable. And like this, the thing is growing and growing without generating large triangles like in the very first try. Great. But still it is not very nice, because the remesh is in charge of keeping the triangle size even, but it cannot resolve self-intersections, like here, for example. There the stuff just grows and intersects itself. So how can we solve this? Well, in Houdini there is another way of remeshing. We don't have to use a remesh node, and this other way is even faster. So let's get rid of this remesh node, and instead let's append a VDB from polygons to convert our stuff into a VDB, into a volume. Like so. So now this converts whatever we have here into a VDB. Let's decrease the resolution to give it a little more quality, say 0.05. Now this is the volumetric surface, and converting this to a volume means that we automatically resolve all the self-intersections. Now the next step is to smooth this. So let's lay down a VDB smooth SDF, like so, to smooth this entire thing, to help with the next curvature calculation. And then we convert this back to polygons, because we only use volumes to remesh this thing. So append a convert node and switch it to polygons. Now we are left with this. And I'm curious what happens if we now make the simulation run. And look what happens now. Now this is really interesting, because we now have a volume that is resolving the self-intersections and at the same time is caring about keeping the resolution tied to the surface area. We get a coral-like growing structure. And now, just for visualization purposes, we might want to go in and just lay down an attribute transfer node, attribute transfer, that is capable of moving attributes from one geometry to a different geometry, like so. And if we make this visible, it will transfer CD, just that we see what's going on. And if we now go up, you see where the curvature is high, the stuff is growing. And it's forming this very, very intricate structure here. And if you're not totally happy with this blocky look of the color, you might want to append another attribute blur here after the solver and switch it to CD and maybe up the iterations to 3, like so. Let's get rid of the wireframe display. And now we have a very, very intricate and interesting structure that is growing through a solver process. And of course, it's getting slower and slower because the VDB is growing bigger and bigger and using more and more resolution. But nevertheless, it is showing you the power of simulations. By using the solver, we can use the state of the previous frame, and we can base all our operations to the geometry on the previous frame. And that is a very, very nice thing. One thing is not totally clean, though, with our setup, and that is the very first frame. Because in the very first frame, there is no previous frame. And although it is working, it is not clean. But we can clean it up by introducing one more node, a switch node. What we want to achieve is that it is reading the stuff that is coming in over input 1 on the very first frame, and on the very first frame only, and after that using the values from this previous frame node. And we can achieve this by just connecting these two nodes to the switch, then going to the switch and using an expression here. And this hscript expression reads $f, which is a current frame, equals, which is a comparison operator to say if the current frame is exactly equal to a number, and this number is 1. So whenever this number is 1, so as soon as we are on frame 1, this switch node will default to this input 1 node, and after that, whenever this is not true, it will use the stuff that comes out of the previous frame. So now we resolve the situation, or the boundary condition at frame 1, where we don't have data on the previous frame node. So now let's go up and let's see what this gives us. And it is not giving us anything, and that is because I have to move the display flag down here, because the node that has a display flag is providing the data for the next frame. So the switch node just provided a sphere. Nothing is happening then. And now it is still generating a beautiful coral. And this is really a nice setup, because by altering the parameters, so playing with the blur radii and with the displacement amount, you really can generate a lot of very intricate and interesting organic looking structures. So that is the introduction to DOPs, because the SOP solver is a kind of DOP network. And next time we will dive deeper into DOPs and have a look at simulating objects. So I hope you learned something, and see you next time.